Hi, everybody. Welcome to chapter 15. This is more of a conceptual lecture. So we'll talk about some stuff in chapter 15, and very likely I will be putting up some assignments for 14 and 15 so that you have a chance to look at and work through those. So let's just start with just understanding this conceptually. So chapter 15, the chi or chi, however you want to say it, square statistic test for the goodness of fit and independence. So some learning outcomes we'll talk about today. We will explain when a chi-square test is appropriate, or chi. Test the hypothesis about the shape of a distribution using the chi-square goodness of fit. Test the hypothesis about the relationship between variables using the chi-square test of independence. And evaluate the effect size using the phi coefficient for Cramer's V. Some tools you'll need: proportions, math review, appendix A, frequency distributions, chapter 2. Introduction to chi-square, the test for goodness of fit. Statistical tests used thus far have tested hypotheses about population parameters and are called parametric tests. Parametric tests share several assumptions. First, they share normal distribution in the population, homogeneity of variance in the population, numerical score for each individual, and those also require data from an interval or ratio scale. Some more things to think about in terms of parametric and non-parametric statistical tests. If the research situation does not conform to the requirements of a parametric test, a non-parametric test is needed. This is an alternative to a parametric test. It does not state the hypotheses in terms of a specific population parameter. This also makes few assumptions about the population distribution-free tests. Two non-parametric tests use chi-squares. Continuing on, non-parametric tests usually classify participants into categories. These categories are usually nominal or ordinal scales. Non-parametric test data may be frequencies such as the number of Republicans or Democrats in a town. Sometimes it is not possible to obtain interval or ratio scale measurements, and its undetermined or infinite scores cannot be measured. Undetermined or infinite scores cannot be measured, but can be categorized. Again, some more stuff. You have a choice of statistical procedure determined primarily by the level of measurement. You could choose to test the significance of the relationship, which would be your chi-square, your t-test, or your ANOVA. You could also choose to evaluate the strength of the relationship with R squared. The chi-square test for goodness of fit. The chi-square test answers research questions about the proportions or relative frequencies for a distribution. This uses sample data to test hypotheses about the shape or proportions of a population distribution. This tests the fit of the proportions in the obtained sample with the hypothesized proportions of the population. Figure 15.1, this is a distribution of exam grades for a sample of n equals 40 individuals. The same frequency distribution is shown as a bar graph as a table and with the frequencies written in a series of boxes. The null hypothesis for the goodness of fit test. This specifies the proportion or percentage of the population in each category. This is the rationale for null hypotheses. No preference, equal proportions among categories, or no difference in a specified population from the proportions in another known population. Again, no difference in a specified population from the proportions in another known population. Continuing on, because the null hypothesis for the goodness of fit test specifies an exact distribution for the population, the alternative hypothesis simply states that the population distribution has a different shape. This could be as brief as not null hypothesis. This is often equivalent to population proportions are not equal to the values specified in the null hypothesis. There is no need to calculate a sample mean or sum of the squares for the data for the goodness of fit test. Individuals are classified or counted in each category: grades, exercise frequency, etc., for example. The observed frequency is tabulated for each measurement category, which is your classification. Each individual is counted in one and only one category, which again is classification. Expected frequencies. Goodness of fit test compares the observed frequencies from the data with the expected frequencies predicted by the null hypothesis. Determine expected frequencies that are in perfect agreement with the null hypothesis. The expected frequency is the frequency value that is predicted from the null hypothesis and the sample size, or n. It represents an ideal hypothetical sample distribution. The chi-square statistic. Our notation, x squared, is the symbol for the chi-square statistic. FO is a set of observed frequencies. FE is a set of observed frequencies. And our chi-square statistic is the following formula. X squared is equal to the sum of FO minus FE squared divided by FE. The numerical value of the chi-squared is a measure of the discrepancy between the observed frequencies data and the expected frequencies. In this case, the proportions of observed frequencies in the sample are not expected to be exactly equal to the proportions in the population. A small chi-square value means a good fit between the data and the null hypothesis. The chi-square distribution of degrees of freedom. The null hypothesis should not be rejected when the discrepancy between the observed and expected values is small. It should be rejected when the discrepancy between the observed and expected values is large. The chi-square distribution includes values for all possible random samples when the null hypothesis is true. All chi-square values are greater than or equal to 0. When the null hypothesis is true, sample x squared values should be small. The chi-square distribution and degrees of freedom. The chi-square distribution is positively skewed. The chi-square is a family of distributions. Distributions are determined by the degrees of freedom, slightly different shape for each value of degrees of freedom. Degrees of freedom for goodness of fit test. Degrees of freedom is equal to C minus 1. C is, of course, the number of categories. Degrees of freedom is not related to sample size, or n. This is figure 15.2. A chi-square distributions are positively skewed. The critical region is placed in the extreme tail, which reflects large chi-square values. Figure 15.3. The shape of the chi-square distribution for different values of degrees of freedom. As the number of categories increases, the peak mode of the distribution has a larger chi-square value. Locating the critical region for a chi-square test. First, determine the significance level, or the alpha. Then locate the critical value of the chi-square in a table called the chi-square distribution. You can find this in Appendix B. Next, values for the degrees of freedom, df, in the first column. Significance level chosen, alpha, in the top row. Critical values of chi-square are the numbers listed in the body of the table. A portion of the chi-square distribution is presented in table 15.1. Figure 15.4. For example, 15.2, the critical region begins at a chi-square value of 7.81. Reporting the results for chi-squared. The report should describe whether there were significant differences between categories. The report should include x squared, degrees of freedom, sample size, n, and test statistic value, significance level. For example, x squared times 3, n equals 50 is equal to 9.36, p is less than 0.05. The report may also provide the observed frequencies for each category. Goodness of fit and the single sample t-test. Non-parametric chi-squared test versus a parametric t-test. The chi-squared test for goodness of fit makes no assumptions about the parameters of the population distribution. The t-test assumes a normal population, requires numerical scores, and tests hypothesis about the population mean, or the parameter. Similarity. Both the goodness of fit and single sample t-test. One similarity is both tests use the data from a single sample to test hypotheses about a single population. The level of measurement determines the test. Numerical scores, interval, or ratio scale make it appropriate to compute a mean and use a t-test. Classification in non-numerical categories, ordinal or nominal scale, makes it appropriate to compute proportions or percentages and to use a chi-square test. Learning check 1. The expected frequencies in a chi or chi-square test are always whole numbers, can contain fractions or decimal values, can contain both positive or negative values, or can contain fractions and negative numbers. Well, the expected values and frequencies in a chi-square test can contain fractions or decimal values. Decide if each of the following statements is true or false. True or false. In a chi-square test, the observed frequencies are always whole numbers. True or false. A large value for a chi-square will tend to retain the null hypothesis. Our first one is true. Observed frequencies are just frequency counts, so there can be no fractional values. Our second one is false. Large values of chi-square indicate that observed frequencies differ a lot from null hypothesis predictions. The chi-square test for independence. The chi-square statistic can also test for evidence of a relationship between two variables. Each individual jointly classified on each variable. Counts are presented in the cells of a matrix. The design may be experimental or non-experimental. Frequency data from a sample are used to test the evidence of a relationship between the two variables in the population using a two-dimensional frequency distribution matrix. The null hypothesis for the test of independence. The null hypothesis, the two variables are independent, no relationship exists. There's two versions or two ways to look at this. The single sample with each individual measured on two variables, there is no relationship. Or two or more separate samples, no difference between distribution of variable in the two populations or same proportions. Variables are independent if there is no consistent predictable relationship. So under the second version of the null hypothesis does not say that the two distributions are identical. Instead, it says that they have the same proportions. Also, stating that there is no relationship between variables, version 1, is equivalent to stating that the distributions have equal proportions. Observed and expected frequencies. Frequencies in the sample distribution are the observed frequencies for the test. Expected frequencies are based on the null hypothesis prediction of the same proportions in each category or the population. Expected frequency of any cell is jointly determined by its column proportion and its row proportion. A simple formula for determining expected frequencies. Frequencies computed by the same method for any cell in the frequency distribution matrix looks like the following. FC is the frequency total for the column. FR is the frequency total for the row. N is the number of individuals in the entire sample. That's how you get FE, or the expected frequency. The chi-square statistic and degrees of freedom. The same equation for the chi-square test of independence as the goodness of fit, which we looked at before. You have your chi-square statistic, and then of course you have your degrees of freedom, which is equal to R minus 1 and C minus 1. R is the number of rows, C is the number of columns. So how do we go about this? Well, here's how we go about it. A summary for the chi tests for independence. The test for independence uses the same procedures as the other tests. There's 4 steps. Step 1, state the hypotheses and select an alpha level. Step 2, locate the critical region. Step 3, compute the test statistic. Step 4, make a decision. Effect size and assumptions for the chi-square test. A significant chi-square hypothesis test shows that the difference did not occur by chance. Tests of significance are influenced not only by the size or strength of the treatment effects, but also by the size of the samples. The outcome of a hypothesis test should be accompanied by a measure of the effect size. We can use Cohen's W. Cohen's W can be used to measure the effect size for both types of chi-square tests. And here is your equation. The PO values are the observed proportions. And that is your equation right there. Again, today, just try to understand it conceptually. I'll work on seeing if I can come up with some additional ways in which you guys can understand this. So again, just think about it conceptually right now. Cohen suggested that 0.10 is a small effect, 0.30 a medium effect, and 0.50 a large effect. Cohen's W does not use the sample size. Therefore, the sample size does not affect the value of W. W is calculated using only the sample proportions and the proportions from the null hypothesis. W and chi-square are algebraically related. The phi coefficient parameter is V. For a 2x2 matrix, each variable has exactly two values. The phi coefficient measures the strength of the relationship. So the phi coefficient is a proportion of variance accounted for, just like R squared. For a larger matrix, a modification of the phi coefficient is used to measure effect size, Kramer's V, and this is our formula right here. Degrees of freedom is the smaller of either R minus 1, which is your row, or C minus 1, which is your column. So table 15.8, some standards for interpreting Kramer's V as proposed by Cohen. And this is just the standards we talked about. Small effect for each degree of freedom, 1, 2, and 3. Medium effect, and of course, large effect. Some assumptions and restrictions for a chi-square test. Several conditions must be satisfied to use a chi-square test for goodness of fit or a test of independence. First, independence of observations. Each observed frequency is generated by a different individual. 2, size of expected frequencies. The chi-square test should not be performed when the expected frequency of any cell is less than 5. Learning check 3. A basic assumption for a chi-square test hypothesis test is the population distributions must be normal, or the scores must come from an interval or ratio scale, or the observations must be independent, or none of the other choices are assumptions for chi-square. So our answer is a basic assumption for a chi-square hypothesis test is the observations must be independent. Decide if each of the following statements is true or false. True or false, the value of degrees of freedom for a chi-square test does not depend on the sample size n. True or false, a positive value for the chi-square statistic indicates a positive correlation between the two variables. Number 1, true. The value of the degrees of freedom for a chi-square test depends only on the number of rows and columns in the observation matrix. False. Chi-square cannot be a negative number, so it cannot accurately show the type of correlation between the two variables. This is what the SPSS output looks like for the chi-square test for independence in example 15.3. So your chi squared, your continuity correction, your likelihood ratio, number of valid cases, and here's our variance and cross tabulation up here. Again, this is another example of SPS output. This example is listed on page 564. A 0.0 have expected count less than 5. The minimum expected count is 9.29. B computed only for a 2x2 table. And of course, if you have questions, concerns, etc., please do reach out. Again, today was just more of an overview to get a sense of the material and understand it conceptually. I will work on getting more stuff out to you that explains it in greater depth. Hope you learned something. Take care, and I will see you in the next video.